Hello. Imagine for a moment that you are looking at a perfectly constructed labyrinth, or a complex, intricate knot made of silk. At first glance, it seems like a contradiction, a tangle that shouldn't be possible. But as you look closer, and you patiently trace the paths, you realize that the knot holds a hidden, elegant logic. The labyrinth has a solution. That's what a paradox is. It's not a dead end for thought. It's an invitation. It's a quiet, gentle whisper from the universe that says, your intuition is a little too simple for what's really going on here. Look closer. A paradox is where our common sense breaks down, and in that breaking, we often find a much deeper and more beautiful truth about the nature of reality. So tonight, we are not going to be solving equations or getting frustrated by contradictions. We are simply going to take a quiet walking tour through a grand museum of these cosmic puzzles. We will admire their strangeness, we will appreciate the profound questions they ask, and we will let our minds drift with the quiet wonder of it all. This is not a journey for answers, but a journey to appreciate the beauty of the questions themselves. Let's begin our tour in the first gallery, a hall dedicated to the most fundamental and personal things we know, time and space. Our first exhibit is perhaps the most famous and most elegant paradox in all of physics. It's a quiet story about two twins, a fast spaceship, and the strange, flexible nature of time itself. This is the twin paradox.
The story is a simple one. Imagine two identical twins. Let's call them Anna and Ben. They are both 20 years old. Anna is an astronaut, and she is about to embark on an incredible journey. She is going to fly a super advanced starship to a nearby star and back. Her ship is capable of traveling at nearly the speed of light, say 99.5% the speed of light. Ben, her brother, is going to stay behind on Earth. Anna says her goodbyes, climbs aboard her sleek starship, and blasts off into space. From Ben's perspective on Earth, her journey is a long one. The star she is visiting is about 10 light years away. So, for Ben, the round trip takes just over 20 years. He lives his life. He goes to school, gets a job, maybe starts a family. He gets older. He tracks his sister's journey, and after 20 long years have passed on Earth, he gets the message that her ship is returning. He is now 40 years old, and he goes to the spaceport to welcome his sister home. The ship lands, the hatch opens, and out walks Anna. But she is not 40 years old. She looks almost exactly as she did the day she left. For her, on that fast-moving ship, time itself was moving much more slowly. According to the mathematics of Einstein's special relativity, at 99.5% the speed of light, time for her would have passed 10 times slower than for Ben. So while 20 years passed for him on Earth, only about 2 years passed for her. She is now 22 years old, and her twin brother is a middle-aged man of 40. This is the strange and well-proven reality of time dilation. Time is not absolute. It is relative to your motion. The faster you move through space, the slower you move through time.
The paradox arises when you try to look at the situation from Anna's point of view. From her perspective on the spaceship, she is the one who is sitting still, and it is the Earth, with her brother Ben on it, that is moving away from her at 99.5% the speed of light. So, according to her, shouldn't Ben's clock be the one that is running slow? Shouldn't she return to find that Ben is the one who has aged less? How can they both be younger than each other? It seems like a complete contradiction. This is the beautiful puzzle of the twin paradox. And the solution is incredibly elegant. The two twins are not in a symmetrical situation. While it's true that from a constant velocity all motion is relative, Anna's journey was not one of constant velocity. To get to the star, she had to accelerate to an incredible speed. When she got there, she had to slow down, turn around, and then accelerate again to come back. And when she got back to Earth, she had to decelerate to land.
It is this acceleration, the turning around part, that breaks the symmetry. Anna is the one who has undergone acceleration, who has changed her inertial frame of reference. Ben on Earth has not. It is this act of turning around that makes her the traveling twin in a real physical sense. And so, she is the one who truly experiences less time. The paradox dissolves, and we are left with a profound truth. Time travel into the future is physically possible. If you want to see the Earth in the year 3000, you just need a very, very fast spaceship. It's a quiet, mind-bending consequence of the universe's strange geometry. Let's now move to our next exhibit in this gallery, another quiet puzzle from Einstein's theory of special relativity. This one is about space rather than time. It's called the ladder paradox, or sometimes the barn paradox. Imagine, if you will, a long ladder, say 10 meters long, and you have a barn with two doors, a front door and a back door, that is only 8 meters long. Now, if the ladder is at rest, you can clearly never fit it inside the barn and close both doors at the same time. It's just too long. But what if you start running with the ladder at an incredibly high speed, say 80% the speed of light? According to special relativity, objects that are moving at relativistic speeds experience length contraction in the direction of their motion. From the perspective of a stationary observer, let's say a farmer standing by the barn, the fast-moving ladder will appear to be shorter. At 80% the speed of light, the 10-meter ladder would appear to be contracted down to only 6 meters long. So the farmer would see the 6-meter ladder easily fit inside the 8-meter barn. The farmer could, in theory, close the front door right after the back of the ladder has entered, and then open the back door just before the front of the ladder hits it. For a brief, fleeting instant, the contracted ladder would be completely contained inside the barn with both doors shut. But now here comes the paradox. Let's look at it from the perspective of the person running with the ladder. From their point of view, the ladder is at rest, and it is the barn that is rushing towards them at 80% the speed of light. So from their perspective, the ladder is its normal 10 meters long, but the barn is the thing that is length contracted. The 8-meter barn would appear to be squished down to less than 5 meters long. From the runner's perspective, there is absolutely no way their 10-meter ladder could ever fit inside a 5-meter barn. So who is right? Can the ladder fit inside the barn, or can't it?
The resolution to the ladder paradox is just as elegant as the solution to the twin paradox, and it reveals another deep truth about our universe. The key is that both the farmer and the runner are correct from their own frame of reference. The paradox arises because of a faulty assumption we all make, that simultaneity is absolute. We assume that two events that happen at the same time for one observer must happen at the same time for all observers. But Einstein showed that this is not true. For the farmer standing by the barn, the two events, the front door closing and the back door opening, can happen at the same time while the ladder is momentarily inside. But for the person running with the ladder, these two events do not happen at the same time. From their perspective, because of the strange effects of relativity, the front door of the barn closes, and then, a fraction of a second later, the back door opens. They never see both doors closed at the same time with the ladder inside. So the ladder does fit inside the barn from the farmer's point of view, and it does not fit inside the barn from the runner's point of view. And both are right. There is no single objective truth about the situation. It depends entirely on your frame of reference. The paradox dissolves when we let go of our intuitive but incorrect notion of a universal now. It's a quiet, profound lesson that space, time, and even the order of events are not as fixed as they seem. Now, for our final brief stop in this gallery, we touch upon the most famous paradox of all, one that is more a part of science fiction, but is a wonderful puzzle for thought. This is the grandfather paradox. The idea is simple. If you were to build a time machine and travel back in time to meet your grandfather as a young man,
What would happen if you were to, say, prevent him from meeting your grandmother? If he never meets your grandmother, then you are never born. But if you are never born, then you could never have gone back in time to prevent them from meeting in the first place. It's a perfect, self-negating logical loop. This paradox is one of the main reasons why most physicists believe that time travel to the past is likely impossible, as it seems to violate the fundamental law of causality. All right, let's leave the strange, bending worlds of relativity behind us. We'll now move into a new hall in our quiet museum, one dedicated to paradoxes that we can see with our own eyes when we look up at the sky. These are the contradictions between what we observe and what our simple models would predict. They are quiet puzzles hidden in the starlight. Our first and most fundamental exhibit here is one we have touched on before, but it deserves a deeper look. It is perhaps the oldest cosmological paradox of all. This is Olbers Paradox, named after the 19th century German astronomer Heinrich Olbers, though the idea had been discussed by many thinkers before him. The paradox begins with a very simple question, the kind a child might ask, but one that has profound implications. Why is the night sky dark? At first, this sounds like a silly question. The sky is dark at night because the sun is on the other side of the planet. But Olbers considered what the sky would look like in a universe that was infinite, eternal, and uniformly filled with stars, which was the prevailing view for a very long time. Let's think about it quietly. If the universe stretches on forever in every direction and is filled with an infinite number of stars, then no matter where you look in the sky, your line of sight should eventually end on the surface of a star. It might be a very, very distant star, but in an infinite universe, it has to hit one eventually. It's like being in a forest that goes on forever. No matter which direction you look, you will eventually see a tree. So, if this were true, the entire night sky, every single point, should be as bright as the surface of a star. The night should be as blindingly bright as the day. But it's not. It's dark. This simple, profound observation is the paradox.
The resolution to Olbers' paradox is one of the most powerful and beautiful pieces of evidence for our modern understanding of the cosmos, the Big Bang Theory. The darkness of the night sky tells us that the universe is not infinite and eternal in the way that people used to think. The first part of the solution is that the universe has a finite age. It began about 13.8 billion years ago. This means that we can only see the light from stars and galaxies that are within a certain distance of us, a distance of 13.8 billion light years. The light from any stars that are farther away than that simply has not had enough time in the entire history of the universe to reach us yet. So our observable universe is not infinite. There is a horizon beyond which we cannot see, which limits the number of stars whose light can reach us. The second and equally important part of the solution is that the universe is expanding. And because it's expanding, the light from very distant galaxies gets stretched out as it travels through that expanding space. This stretching of light waves shifts them to lower energies and longer wavelengths, a phenomenon we call redshift. For very distant galaxies, their visible light is redshifted so much that it moves into the infrared and microwave parts of the spectrum, which our eyes cannot see. So, the darkness of the night sky is not a sign of emptiness. It is a profound and beautiful testament to the history of our universe. It is the visible evidence that our universe had a beginning, and that it has been expanding ever since that moment of creation. The simple act of looking up into a dark, peaceful sky is an act of cosmology.
Now let's turn from the darkness of the night sky to the brightness of our own young sun for our next quiet paradox. This one is called the faint young sun paradox. Our modern understanding of stellar evolution tells us, with a great deal of confidence, how stars like our Sun change over their long lifetimes. Our models predict that when our Sun was a young star, about 3 to 4 billion years ago, it was significantly dimmer and cooler than it is today. It would have been only about 70% as luminous as it is now. This isn't a speculative idea. It's a fundamental consequence of how stars fuse hydrogen in their cores. Now, here is the paradox. If the Sun was 30% dimmer back then, the Earth should have been receiving much less energy. Climate models based on this dimmer Sun consistently show that the early Earth should have been completely frozen over. It should have been a solid ice ball, a snowball Earth, with global temperatures well below the freezing point of water. But when we look at the geological record from that same period, we find the exact opposite. We have ancient rock formations, some over 3.5 billion years old, that show clear evidence of having been formed in liquid water. We see signs of ancient riverbeds, sedimentary layers from ancient lakes, and even pillow lavas, which are a type of rock that only forms when lava erupts underwater. So the geological evidence tells us that the early Earth was not a frozen wasteland. It was warm and wet and had vast, stable liquid water oceans. How could the Earth have been warm enough for liquid water when it was orbiting a much fainter sun? This is the faint young sun paradox.
The solution to this paradox is not yet fully settled, but it likely lies in the nature of Earth's early atmosphere. While the sun was fainter, our planet's atmosphere was very different. It was much thicker and contained a much higher concentration of greenhouse gases. The early Earth's atmosphere had very little oxygen, but it was rich in gases like carbon dioxide, methane, and ammonia, all of which are incredibly potent greenhouse gases. This thicker, more insulating atmospheric blanket would have trapped a much larger portion of the faint sun's heat, keeping the planet's surface warm enough for liquid water to exist. It's like the Earth had a much heavier winter coat on to compensate for the weaker fire. As the sun has slowly brightened over billions of years, the composition of our atmosphere has also changed. The rise of photosynthetic life pumped oxygen into the air, and geological processes have slowly removed much of the carbon dioxide, thinning out the greenhouse blanket. This suggests that there has been a delicate, long-term balancing act between the sun's increasing luminosity and the Earth's decreasing greenhouse effect, which has kept our planet's climate remarkably stable for billions of years. It's a quiet, beautiful idea that the habitability of our world is the result of a long, slow dance between geology, biology, and astronomy. Now, let's leave our own sun and travel to a nearby star system for our next celestial contradiction. This is a classic puzzle in stellar evolution known as the Algol Paradox.
The star Algol, located in the constellation Perseus, has been known for centuries as the demon star because it appears to wink, changing its brightness on a regular, predictable schedule. We now know that Algol is not a single star, but a binary star system with two stars orbiting each other. The winking is simply one star passing in front of the other from our point of view, causing a partial eclipse. But when astronomers in the 20th century were able to measure the properties of the two stars in the Algol system, they found something that seemed to violate the fundamental laws of stellar evolution. The system consists of a very massive, hot blue main sequence star and a smaller, less massive, but much more evolved subgiant star. And this is the paradox. According to everything we know about how stars live and die, the more massive a star is, the faster it burns through its fuel, and the more quickly it evolves. So in the Algol system, the massive blue star should have been the first one to evolve off the main sequence and become a giant. But what we see is the opposite. The less massive star is the one that is more evolved. It's as if in a family with two siblings, the younger brother was somehow much older than his big sister. It made no sense. The solution to the Algol paradox is a beautiful piece of cosmic detective work that introduced a new and important idea into astronomy: mass transfer between stars. The original theory was correct. The less massive star did start out as the more massive one. As it aged and swelled up into a red giant, its outer layers expanded so much that they reached the gravitational pull of its smaller companion star. The smaller star then began to feed on its larger neighbor, siphoning off a huge amount of hydrogen gas through a stream of material connecting the two.
Over millions of years, this process completely reversed their roles. The originally more massive star had so much of its mass stolen that it became the less massive of the two. And the originally smaller star, having feasted on all that fresh hydrogen from its companion, became the more massive star we see today. So the paradox is solved. The evolved-looking star is older, it just lost a lot of weight. And the young-looking star has just had a very big meal. The Olbers Paradox is a quiet, elegant story of stellar companionship and cosmic cannibalism, and it taught us that stars and binary systems can have very strange and interactive lives. Our final stop in this gallery of celestial contradictions takes us back to the very beginning of the universe. This is a subtle but persistent puzzle known as the cosmological lithium problem. Our theory of the Big Bang is incredibly successful. It makes very precise predictions about the state of the early universe. Specifically, a process called Big Bang nucleosynthesis, which occurred in the first few minutes after the Big Bang, predicts the exact abundance of the first light elements that should have been created. The theory predicts that the early universe should have been about 75% hydrogen, 25% helium, and a tiny, tiny trace amount of lithium. When we look out into the universe, the predictions for hydrogen and helium match what we observe with incredible accuracy. It's one of the great triumphs of the Big Bang model. But there's a problem with the lithium. When we look at the oldest, most metal-poor stars in our galaxy to see what the primordial abundance of elements was, we find that they have only about 1/3 the amount of lithium that the Big Bang theory predicts. There seems to be a significant amount of missing lithium in the universe. This discrepancy is the cosmological lithium problem.
So where did the lithium go? This is a quiet, nagging puzzle at the heart of cosmology. There are two main possibilities. The first is that there is something we don't understand about the old stars themselves. Perhaps these first-generation stars have some unknown process in their interiors that efficiently destroys lithium over their long lifetimes. We might be looking at stars whose original lithium content has been altered. The other, more exciting possibility is that there is something slightly wrong with our understanding of the Big Bang itself. Perhaps there was some unknown particle or interaction in the very early universe that affected the rate at which lithium was produced. Solving this quiet little paradox could open up a window into new physics, beyond our current standard model. It's a subtle clue, a small crack in our otherwise incredibly successful model of the cosmos that hints that there are still deep mysteries waiting to be understood about the first few minutes of time. All right, let's take a breath and leave the paradoxes of the visible sky behind us. We are now descending into a deeper and darker wing of our museum. This is the gallery of impossible objects, places where gravity becomes so extreme and matter so dense that our familiar laws of physics begin to fray and tear. This is the realm of black holes. We begin with the most famous paradox in modern physics, a deep and profound conflict between our two greatest theories of the universe. This is the black hole information paradox.
To understand this paradox, we need to appreciate the two pillars of modern physics. On one hand, we have Einstein's general relativity, our theory of gravity and the large-scale universe. On the other hand, we have quantum mechanics, our theory of the very small, the world of particles and atoms. Both theories are spectacularly successful in their own domains, but when you try to bring them together in the extreme environment of a black hole, they seem to give completely contradictory answers. The paradox revolves around the concept of information. In physics, information isn't just words or data, it's the unique, specific quantum state of every single particle. It's all the properties that make a particle what it is. And a fundamental, unbreakable law of quantum mechanics is that information can never, ever be truly destroyed. It can be scrambled, rearranged, or hidden, but it can't be erased from the universe. If you burn a book, for example, the information that made up the book is not gone. It's just transformed into the complex arrangement of the ash, the smoke, the heat, and the light. In theory, a powerful enough computer could track all of that and reconstruct the original book. But now consider a black hole. According to general relativity, a black hole is a very simple object. It has an event horizon, a one-way door from which nothing can escape. Anything that falls into a black hole is, according to the theory, eventually crushed down to an infinitely small, infinitely dense point at the center, the singularity. And in that singularity, all the intricate information about the things that fell in seems to be completely and permanently erased from the universe. This is a direct violation of the laws of quantum mechanics. So which theory is right?
For a long time, physicists could kind of sweep this problem under the rug. The information wasn't really destroyed, they could argue. It was just locked away forever inside the black hole. Inaccessible, but still technically there. But then, in the 1970s, Stephen Hawking made a discovery that made the paradox inescapable. He showed that due to quantum effects at the event horizon, black holes are not completely black. They should slowly radiate energy away into space, a phenomenon we now call Hawking radiation. This means that over an immense period of time, a black hole will slowly evaporate and eventually disappear completely. So, what happens to the information that was inside it? Hawking's initial calculations suggested that the radiation that comes out is completely random and thermal. It contains no trace of the specific information about the things that fell in. So when the black hole is completely gone, the information seems to be truly, permanently erased from the universe. This is the black hole information paradox in its full, baffling glory. It is a deep and fundamental conflict between our two best descriptions of reality. Solving it is one of the biggest goals of theoretical physics. It has led to some of the most profound and strange ideas in science, like the holographic principle, the idea that all the 3D information of what falls into a black hole might be somehow encoded on its 2D event horizon, like a cosmic hologram. It's a quiet, beautiful puzzle that tells us we are still missing a crucial piece of the puzzle, a unified theory of quantum gravity.
Now for a related but more subtle black hole puzzle. This is the no-hair theorem paradox. It's a wonderful name for a very elegant idea. The no-hair theorem is a consequence of general relativity that states that a stable black hole is an incredibly simple object. After it forms and settles down, it is defined by only three and only three properties: its mass, its spin or angular momentum, and its electric charge. That's it. Any other hair, any other complex information about what it was made from, whether it was stars, planets, or teapots, is lost forever behind the event horizon. The paradox arises when you consider this idea in the context of the second law of thermodynamics, one of the most fundamental laws of physics. This law states that the total entropy, or disorder, of a closed system can never decrease. Things always tend towards more disorder. A clean room will naturally get messy. A hot cup of coffee will always cool down, its ordered heat energy dissipating into the disordered air. But a black hole seems to violate this. You can take a very hot, messy, high-entropy star and collapse it into a perfect, simple, no-hair black hole, which seems to have almost zero entropy. You've just taken a very disordered system and made it very ordered, seemingly destroying entropy and violating a fundamental law of physics. This was a huge puzzle.
The solution was proposed by the physicist Jacob Bekenstein and later proven by Stephen Hawking. They realized that the entropy of a black hole isn't zero. It is in fact enormous. And its entropy is proportional not to its volume, but to the surface area of its event horizon. When you throw something into a black hole, the tiny increase in its mass increases its surface area just enough to account for the entropy of the object you threw in. So the total entropy of the universe always increases. It's a beautiful solution that connects gravity, thermodynamics, and quantum mechanics, and it's what led Hawking to his discovery of black hole radiation.
Our next paradox is a more modern one, a strange wrinkle that has emerged from trying to reconcile the weirdness of quantum mechanics with the nature of the event horizon. This is the black hole firewall paradox. The story starts with one of Einstein's key principles, the principle of equivalence. It states that an observer in free fall should not feel the effects of gravity. If you were falling into a black hole, as you cross the event horizon, you shouldn't feel anything special. It should be a smooth, unremarkable moment of passage. This is the classical general relativity view. However, some modern physicists thinking deeply about the information paradox have argued that quantum mechanics requires something very different to happen. To prevent information from being truly lost, they argue that it must be somehow encoded and radiated back out. One version of this idea suggests that the event horizon itself must be a region of incredibly high energy, a literal firewall of particles that would instantly incinerate anything that tries to cross it. So we have a profound contradiction. General relativity says the event horizon should be a quiet, unremarkable place. Quantum mechanics, at least in some interpretations, seems to say it must be a wall of fire. Both cannot be right. This is the firewall paradox. It is a very active area of debate in theoretical physics. It suggests that there is something very fundamental about either quantum mechanics or our understanding of space-time that we are still missing. It's a quiet, modern puzzle at the very edge of our knowledge, a sign that the story of black holes is far from over.
Let's now pull our view away from the deep mystery of a single black hole and look at the larger scale of galaxies, where we find other quiet statistical paradoxes. Our next exhibit is the dwarf galaxy problem, also known as the missing satellites problem. Our modern theory of how galaxies form is called the lambda CDM model. It's a very successful theory that relies on cold, dark matter, the CDM part, as the invisible scaffolding upon which galaxies are built. Our computer simulations using this model are incredibly good at reproducing the large-scale structure of the universe, the cosmic web of filaments and voids. But when we zoom in on our own local neighborhood, the model seems to break down. The simulations predict that a large galaxy like our Milky Way should be surrounded by thousands of small dwarf satellite galaxies. The gravity of the Milky Way's large dark matter halo should have pulled in countless smaller dark matter halos, each of which should have formed a small galaxy. But when we look at the sky, that's not what we see. We have only found about 50 or 60 small satellite galaxies orbiting the Milky Way. There seems to be a huge discrepancy between the theory and our observation. Where are all the missing dwarf galaxies? This is the dwarf galaxy problem. There are a few possible solutions. Perhaps the simulations are wrong in some subtle way. Or more likely, perhaps those thousands of small dark matter halos did form, but for some reason, they never managed to form stars. Maybe the radiation from the early Milky Way was so intense that it blew away the gas from these small halos before they could ignite into stars. In this case, our galaxy would be surrounded by thousands of dark galaxies, invisible clumps of dark matter with no stars to light them up. It's a quiet puzzle that helps us fine-tune our understanding of how galaxies are truly built.
And a related, equally quiet puzzle is the missing baryon problem. As we've discussed, baryonic matter is just the fancy name for the normal matter that we are made of, protons and neutrons.
Our incredibly successful models of the Big Bang and the early universe make a very precise prediction for how much of this normal matter should have been created. We can see this matter in the early universe by looking at the cosmic microwave background. But when we look at the universe today, at all the stars, all the galaxies, all the clouds of gas and dust that we can see, and we add it all up, we run into a problem. The numbers don't match. The amount of normal matter that we can directly observe in the modern universe only accounts for about half of the baryonic matter that our theories say should be there. So where is the other half of the stuff that makes up you, me, and everything we've ever known? This is the missing baryon problem. For a long time, this was a major puzzle, but in recent years, scientists believe they have finally found the hiding place. It seems the missing matter wasn't really missing, just very, very hard to see. It is thought to be spread out in a vast, incredibly hot, and incredibly tenuous medium that exists in the space between the galaxies. This is the warm-hot intergalactic medium, or WIM. It's a cosmic web of superheated gas that connects the galaxies together. It is so incredibly diffuse, only a few atoms per cubic meter, that it doesn't shine or absorb light in a way that is easy to detect. But recently, using sensitive X-ray telescopes, we have started to find evidence of this vast, hidden reservoir of normal matter, finally solving this quiet, long-standing cosmic puzzle.
All right, let's take a quiet breath. We have explored the strange nature of time and space, the quiet contradictions in our starry sky, and the impossible physics of black holes and galaxies. Now we must zoom our perspective all the way out until our entire galaxy is just a single point of light, and we can contemplate the universe as a single, unified object. It is here, on this grandest of all scales, that we find some of the most profound and fundamental puzzles in all of science. These are the paradoxes that question the very history and structure of our reality. We begin with a beautiful puzzle that comes from looking at the baby picture of our universe. This is the horizon problem. To understand this, we have to think about the cosmic microwave background, or CMB. The CMB is the oldest light in the universe. It's the faint, residual afterglow of the Big Bang, a bath of gentle microwave radiation that fills all of space. When our telescopes, like the Planck satellite, map out this ancient light, they are essentially taking a picture of the universe as it was just 380,000 years after the Big Bang. And this baby picture is remarkably uniform. The temperature of the CMB is almost perfectly the same in every direction we look, at a steady 2.7 Kelvin. The tiny fluctuations in temperature, the little warmer and cooler spots, are only different by 1 part in 100,000. This uniformity is, at first glance, a beautiful confirmation of our cosmological models. But when you think about it more closely, it presents a massive paradox.
Here is the problem. Imagine looking at one patch of the CMB in one direction of the sky, let's say east. Now imagine looking at another patch on the exact opposite side of the sky, west. The light from the east patch has taken 13.8 billion years to travel to us, and the light from the west patch has also taken 13.8 billion years to travel to us. This means that these two regions of space, in the entire history of the universe, have never had time to be in contact with each other. Light has never had time to travel between them. They are outside each other's causal horizon. So how did they know to be the exact same temperature? It's like having two friends, one in London and one in Tokyo, who have never met, never spoken, never exchanged a single message, but who decide to wear the exact same, incredibly specific and detailed outfit on the same day.
It would be an unbelievable coincidence. And yet, this is what we see in every direction we look in the universe. Regions of space that should have never been able to communicate with each other somehow reached a perfect thermal equilibrium. This is the horizon problem. It's a deep puzzle about the initial conditions of our universe. The leading solution to this paradox is a truly mind-bending idea called cosmic inflation. This theory suggests that in the very first tiniest fraction of a second after the Big Bang, the universe underwent a period of incredible, exponential expansion. It grew from a size smaller than a proton to the size of a grapefruit almost instantly.
Before this inflationary burst, the entire region that would become our observable universe was an incredibly tiny subatomic patch. In this tiny state, it was small enough to have been in perfect thermal contact with itself. It had plenty of time to even out its temperature and reach a smooth equilibrium. Then, inflation happened, and this tiny, smooth, uniform patch was suddenly stretched to colossal proportions. The uniformity we see in the sky today, the reason that opposite sides of the universe are at the same temperature, is because they were, in fact, once right next to each other, before being flung apart by this unimaginable burst of expansion in the universe's first moment. It's a wild and beautiful idea that the grand scale of our cosmos is just a magnified image of its once tiny, simple, and uniform self. Now, this theory of inflation also happens to solve our next great cosmological paradox. This is a puzzle about the shape of our universe, known as the flatness problem. According to Einstein's theory of general relativity, space-time can have a shape. Its overall geometry is determined by the total amount of matter and energy within it. There is a critical density of matter and energy. If the universe's actual density is greater than this critical value, then space-time would be positively curved, like the surface of a sphere. This is a closed universe, which would eventually stop expanding and collapse back on itself. If the density is less than the critical value, space-time would be negatively curved, like the surface of a saddle. This is an open universe, which would expand forever. If the density is exactly equal to the critical density, then the universe is perfectly, geometrically flat, like an infinite sheet of paper. And when we make our best measurements of the universe, this is what we find. The density appears to be incredibly, suspiciously close to the critical density. Our universe appears to be perfectly flat.
So why is this a paradox? It's because a flat universe is a very unstable state. It's like trying to balance a pencil perfectly on its sharpest point. Any tiny deviation from perfect flatness at the beginning of the universe should have been magnified enormously over 13.8 billion years of expansion. If the early universe had been just a tiny, tiny fraction denser than the critical density, it would have collapsed back on itself billions of years ago. If it had been just a tiny fraction less dense, it would have flown apart so quickly that galaxies and stars never would have had a chance to form. The fact that we find ourselves in a universe that is so perfectly, exquisitely balanced on the knife's edge of flatness is an incredible coincidence that seems to require an explanation. This is the flatness problem. And once again, the theory of cosmic inflation provides a beautiful and elegant solution. The analogy here is that of an ant living on the surface of a balloon. If the balloon is small, the ant can easily tell that it lives on a curved surface. But now imagine you inflate that balloon to an enormous size, say the size of the Earth. From the ant's tiny perspective, its local patch of the balloon surface would now look completely, perfectly flat. It wouldn't be able to perceive the overall curvature of the balloon anymore. Inflation, the theory suggests, did the same thing to our universe. It took the initial, perhaps very curved geometry of the tiny early universe and stretched it out to such a colossal size that our entire observable universe today is just a tiny patch of this much larger reality. And just like for the ant on the giant balloon, our patch appears perfectly flat to us. The flatness of our universe is, in this view,
just an illusion of scale, a quiet consequence of that incredible burst of expansion at the dawn of time. Now we come to what is arguably the biggest, most profound, and most baffling paradox in all of physics. It has been called the worst theoretical prediction in the history of science. It is a quiet, colossal disagreement between our two best theories of the universe, and we have absolutely no idea how to solve it. This is the cosmological constant problem. Let's unpack this slowly. As we discussed, our observations of distant supernovae in the late 1990s showed that the expansion of the universe is accelerating. Something is pushing everything apart. We call this mysterious force dark energy. Our best model for dark energy is the idea of a cosmological constant, an intrinsic energy that is woven into the very fabric of the vacuum of space itself. It's a property of reality. We can measure the effect of this dark energy. We know how strong it needs to be to produce the acceleration we see, and it turns out to be a very, very tiny but positive amount of energy. So far, so good. The problem arises when we try to calculate what this value should be using our other great theory of the universe, quantum mechanics. Quantum field theory tells us that the vacuum of space is not empty. It's a seething, bubbling foam of virtual particles constantly popping into and out of existence. And all of these virtual particles should have energy. When physicists try to calculate the total energy density of the vacuum based on these quantum fluctuations, they get a number. And this number is not just a little bit wrong. It is outrageously, comically, catastrophically wrong by a factor of 10 to the 120.
The value for the vacuum energy, predicted by quantum mechanics, is about 10 to the power of 120 times larger than the value we actually observe with our telescopes. That is a 1 followed by 120 zeros. It is a number so vast it is difficult to even write down, let alone comprehend. It is without question the largest discrepancy between theory and observation in the entire history of science. If the vacuum energy were really this large, the universe would have been ripped apart by this repulsive force in the first fraction of a second after the Big Bang. The fact that we live in a relatively calm, slowly accelerating universe means that somehow something is canceling out almost all of this predicted vacuum energy, leaving behind just the tiny, delicate amount that we see. What is causing this cancellation? Is there some unknown law of physics, some deep symmetry that we are completely unaware of? Do the effects of all the different quantum fields somehow conspire to cancel each other out with near perfect precision? We simply don't know. The cosmological constant problem is a deep and fundamental crack in our understanding of reality. It tells us that there is a profound disconnect between our theory of the very large, general relativity, and our theory of the very small, quantum mechanics. It is, without question, a quiet, persistent whisper from the universe that we are still missing something very, very big. Our final stop in this gallery of cosmic scale puzzles is a more subtle one. It's a strange, lingering anomaly in our otherwise perfect picture of the early universe. This is the mystery of the CMB cold spot and the axis of evil. As we've said, the cosmic microwave background radiation is incredibly uniform, but it does have tiny temperature fluctuations, which represent the seeds of all the structure we see in the universe today. Our standard model of cosmology predicts that these fluctuations should be completely random, statistically the same in all directions. But when our satellites have mapped them out with incredible precision, they have found a few strange patterns that don't seem to fit. The first is the CMB cold spot.
This is an unusually large and unusually cold patch of the microwave sky. It is a statistical anomaly, a blip that is very unlikely to be just a random chance fluctuation. What could have caused it? One speculative idea is that it could be the bruise left over from a collision between our universe and another bubble universe in a larger multiverse. A more mainstream but still unproven idea is that it's caused by a supervoid, a colossal empty region of space between us and the CMB, which would make the light from that direction appear slightly colder. The second anomaly is the one we touched on before, the so-called axis of evil. This refers to the observation that the largest scale temperature fluctuations in the CMB are not random, but seem to be aligned in a particular direction in space. And what's truly bizarre is that this special direction seems to be aligned with the plane of our own solar system. This seems to violate the cosmological principle, the idea that there should be no special places or special directions in the universe. Most scientists believe this must be a statistical fluke, a coincidence. But it's a quiet, nagging anomaly that hints that there might be something about the universe or our place in it that we do not yet fully understand.
All right, let's take one last quiet breath and descend into the final and deepest gallery of our museum. We have explored the paradoxes of time, space, stars, and the cosmos itself. Now, we will explore the puzzles that touch upon our own existence. These are the paradoxes of life and consciousness. We must begin this final chapter with the king of all existential paradoxes, the one we have already explored in depth but must revisit now as the capstone of our journey. This is the Fermi paradox. As we established at the very beginning of our tour, the universe seems to be perfectly suited for life. There are billions of Earth-like planets in our galaxy alone. The chemical ingredients for life are everywhere, and the universe is very, very old, with billions of years of a head start for life to have evolved elsewhere. So, our galaxy should be teeming with life. It should be a bustling, noisy metropolis of countless civilizations, some of them potentially millions or even billions of years older and more advanced than we are. And yet, when we look and listen, we are met with a profound, unbroken, and what some have called an eerie silence. This is the paradox. In its simplest form, the high probability of extraterrestrial life versus the complete lack of any evidence for it. Where is everybody? Enrico Fermi's simple question still hangs in the air, unanswered. The Great Silence is perhaps the single most profound and unsettling observational fact about our universe, and trying to explain it leads us down some very strange and fascinating paths. Let's slowly walk down a few of them again as a quiet summary of the possibilities. The first great family of solutions to the Fermi paradox is, as we know, the lonely solutions. These argue that the silence is simply because there is no one else to talk to. This brings us back to the idea of the great filter. Perhaps there is some evolutionary or technological barrier that is so incredibly difficult to overcome that almost no species in the universe ever makes it past. Let's just quietly reconsider the possibilities. The filter could be the very beginning of life itself, the leap from non-living chemistry to the first cell, a spark that is almost miraculous. Or the filter could be the leap from a simple microbial cell to a complex one, a biological innovation that took billions of years to happen on Earth and might be a cosmic fluke. Or maybe the filter is intelligence itself, a rare and perhaps not very beneficial evolutionary trait in the long run. And then there's the most sobering possibility of all, that the great filter is still ahead of us, that all intelligent civilizations eventually reach a point where they discover a technology that leads to their own self-destruction.
and that we are currently approaching that same great test. In this view, the silent sky is a quiet, somber warning. Related to this is the rare Earth hypothesis. This suggests there isn't one single great filter, but dozens of smaller ones. It's the idea that for a planet to have a stable environment for billions of years, allowing for the evolution of complex, intelligent life, you need a long, long list of lucky circumstances to all line up perfectly. You need the right kind of star in the right part of the galaxy, with the right kind of unusually large moon to stabilize your climate, and with the right kind of internal geology, like plate tectonics, to regulate your atmosphere. The rare Earth hypothesis suggests that while microbial life might be common, worlds like ours are so fantastically improbable that we might just be the only one in the entire Milky Way.
But what if we are not alone? This brings us to the second great family of solutions, the idea that they exist, but that there is some reason why we can't see them. The simplest of these is the sheer scale of space and time. Maybe civilizations are common, but they are separated by thousands of light years and millions of years of history. The galaxy might be like a string of lights on a Christmas tree that blink on and off independently. The chances of two being on at the same time and also being close enough to see each other might be very small. Then there are the more deliberate sociological explanations. There is the Zoe hypothesis, the idea that advanced civilizations are aware of us but are deliberately hiding, observing us as if we are a protected nature preserve following a strict rule of non-interference. Or there is its darker cousin, the dark forest theory, which posits that the universe is like a dark forest full of silent hunters, and that the only winning strategy is to stay as quiet as possible and eliminate anyone foolish enough to make a sound. In this view, the silence is the sound of universal fear. Or perhaps the problem is with our own perception, the idea that they are too alien to recognize. Maybe they are not biological. Maybe they are vast machine intelligences or planet-sized consciousnesses. Maybe they don't communicate with radio waves, but with some form of physics we don't yet understand. We might be surrounded by their signals, but we are simply not tuned to the right channel. The silence might just be a reflection of our own limited imagination and technology. And this leads us to the final, most mind-bending paradoxes of existence itself, our final exhibits in this quiet tour. This is the strange thought experiment of Boltzmann brains. As we discussed, this is a puzzle that emerges from thinking about the universe on an almost infinite timescale. In the far, far future, in the era of heat death, the universe will be a cold, disordered soup. But quantum fluctuations will still happen, and if you wait long enough, anything that is possible will eventually happen. The paradox, as we explored, is that it is statistically far, far more likely for a single, small, conscious observer, a brain, to spontaneously fluctuate into existence for a brief moment, complete with false memories of a life it never lived, than it is for an entire, vast, low-entropy universe like ours to come into being. This leads to the unnerving philosophical question: how can you be sure that you are not a Boltzmann brain, having a fleeting, illusory experience of a universe that isn't real? It's a quiet, dizzying puzzle that uses the laws of physics to question the very foundation of our own reality. And that brings us to its close cousin, the simulation argument. This is the philosophical idea that, given the likelihood of a civilization developing the technology to create perfectly realistic simulated universes, it is statistically more likely that we are living inside one of those simulations than in the one base reality. It provides a simple, if unsettling, answer to the Fermi paradox. We don't see any aliens because the programmers never wrote them into our particular simulation. It is another unfalsifiable but deeply thought-provoking puzzle. And for our final paradox tonight, let's touch upon the anthropic principle. As we've said, this is the idea that the universe appears to be perfectly fine-tuned for our existence because if it weren't, we wouldn't be here to observe it. It's a selection bias. But it leads to a quiet, unsettling thought. It might mean that our observation of a calm, stable, life-friendly universe is incredibly misleading. We might be living in an extraordinarily rare bubble of stability, and we are, by definition, blind to what a typical universe might be like, which could be far more chaotic and hostile. Our sense of cosmic safety might just be the ultimate illusion of perspective.
And so, our long and quiet journey through the labyrinth of cosmic paradoxes comes to its end. We have wandered from the strange, flexible nature of time and space to the quiet contradictions of our own night sky. We have peered into the impossible heart of a black hole. We have questioned the very structure of our cosmos. And we have finished with the deepest and most personal puzzles of all, the paradoxes of our own existence. What do we do with these ideas? They are not problems to be solved in a single night. They are not worries to keep us awake. They are, I think, a kind of gift. They're the universe's way of gently reminding us of the limits of our own intuition. They are the beautiful, intricate knots in the tapestry of reality that show us where our understanding is still incomplete. And in that incompleteness, there is a profound beauty. A paradox is a signpost. It points us towards deeper truths and new, more elegant ways of seeing the world. The resolution of Olbers Paradox gave us the Big Bang. The resolution of the twin paradox gave us a deep understanding of relativity. And the ongoing struggle with the information paradox and the cosmological constant problem will, someday, likely lead to the next great revolution in physics. So as you drift off to sleep tonight, let your mind be at peace with these quiet puzzles. There is a deep comfort, I think, in accepting that we do not have all the answers. The universe is not a simple story that has already been written. It is a grand, unfolding mystery, and we are lucky enough to be here for a brief moment to witness a small part of it and to ask these wonderful questions. The beauty is not in the solution, but in the search. The wonder is not in the answer, but in the question itself. Sweet dreams.
Let's drift back for a moment to that very first gallery, to the paradoxes of relativity. The twin paradox is so wonderfully counterintuitive, it's worth lingering on. The key, as we said, is the acceleration. But what does that really mean for the twins? Imagine the moment Anna returns. For Ben, 20 years have passed. He has memories of 2 decades of life on Earth. He has seen seasons change, friends and family age, and the world transform around him. His world line, his path through the 4 dimensions of space-time, has been a relatively straight, simple line through time. For Anna, her experience has been completely different. During her 2 years of ship time, she has felt the powerful forces of acceleration pushing her back into her seat. She has felt her ship slow down and physically turn around. Her path through space-time has not been a straight line, but a sharp, bent curve. And a fundamental rule of relativity is that a curved path between 2 points in space-time is always shorter than a straight one. It's the opposite of our intuition about geometry on a flat piece of paper. In the strange geometry of space-time, the person who takes the detour through space actually travels a shorter path through time. The experience of time itself is personal. There is no universal clock ticking away for the whole cosmos. Every observer has their own clock, and the rate at which it ticks depends on their motion and their position in a gravitational field. This is not a theory or a speculation.
It is a measurable, physical reality. The GPS satellites that orbit the Earth have to constantly adjust their own internal clocks to account for both their high speed, which slows their time down, and the weaker gravity they experience, which speeds their time up. So every time you use your phone to find your way, you are quietly using the strange and beautiful truth at the heart of the twin paradox.
And what about the latter paradox? The resolution lies in the relativity of simultaneity, the idea that there is no universal now. Let's think about that more quietly. Imagine you're standing in the middle of a long train car. At the exact same moment, a flash of light goes off at the front of the car and at the back of the car. Since you are in the middle, the light from both flashes reaches your eyes at the same instant, and you would say the two events were simultaneous. But now imagine your friend is standing on the platform, watching your train speed past. From their perspective, as the light from the two flashes travels towards you, you are moving towards the light from the front of the car and away from the light from the back of the car. So from your friend's perspective on the platform, the light from the front flash will reach you before the light from the back flash does. They would say the two events were not simultaneous. Who is right? You both are. Simultaneity is not an absolute property of the universe, it is relative to the observer. And this is the key to the ladder in the barn. The farmer sees the front of the ladder enter and the back of the ladder enter, and he can time the closing of his two doors to be simultaneous in his frame of reference. But for the runner, those two door closings are not simultaneous events. One happens before the other. It's a profound and quiet breakdown of our most basic intuition about the world. It tells us that reality is a much more personal and subjective experience than we ever thought, a tapestry woven from countless different but equally valid points of view.
Let's drift back to the gallery of celestial contradictions and spend more time with the faint young sun paradox. The idea that Earth's early atmosphere was a much thicker greenhouse blanket is the leading solution, but the details are a fascinating puzzle that scientists are still working on. What would that ancient sky have looked like? With much more carbon dioxide and methane and very little oxygen, the sky would not have been the familiar deep blue we know today. It would likely have been a hazy, pale orange, or perhaps even a reddish color, similar to the sky on Saturn's moon Titan. The sunlight filtering through this thick, hazy atmosphere would have been dimmer and more diffuse. The puzzle is how to maintain that perfect balance for billions of years. As the sun slowly brightened, the greenhouse effect on Earth needed to slowly weaken at a corresponding rate to keep the planet's temperature stable. This suggests a long-term, self-regulating climate system. The carbonate-silicate cycle, which we touched on before, is a key part of this. It acts as a planetary thermostat. If the Earth gets too warm, rainfall increases, which pulls more CO2 out of the atmosphere, cooling the planet down. If the Earth gets too cold, volcanic activity continues to pump CO2 into the air, but less of it is removed by rainfall, so the greenhouse effect increases, warming the planet up. But was this cycle enough on its own? Some scientists believe that the emergence of life itself was a crucial factor. Early microbial life, like methane-producing organisms, could have significantly altered the composition of the atmosphere, adding to the greenhouse effect and helping to keep the young planet warm. It's a beautiful idea that life didn't just arise on a habitable planet, but that life itself has actively helped to keep the planet habitable for billions of years in a long, quiet partnership with the geological and astronomical forces at play.
Let's revisit the black hole information paradox. This is truly one of the deepest and most profound puzzles in all of science, and it's worth dwelling on its implications. The conflict between quantum mechanics and general relativity here is absolute. It's not a small disagreement, it's a fundamental contradiction about the nature of reality. Let's think about what information really means in this context. Imagine you have a single hydrogen atom. The information of that atom is everything that makes it what it is. The quantum state of its electron, the spin of its proton, its exact position and momentum. Now, if you throw that atom into a black hole, what happens to that information? According to relativity, the black hole just gets a tiny bit more massive. The specific details of the atom are gone, crushed at the singularity. According to quantum mechanics, that information cannot be lost. It must be preserved somehow. The holographic principle is one of the most compelling, though deeply strange proposed solutions. It suggests that the three-dimensional reality we experience might be an illusion, a projection of information that is stored on a two-dimensional surface at the very edge of the universe. In this view, when you throw the atom into the black hole, its 3D form is destroyed, but its fundamental 2D information gets smeared out and encoded on the surface of the event horizon. Then, as the black hole evaporates via Hawking radiation, that information is slowly and subtly encoded back into the outgoing particles, preserving it perfectly. This would mean that the inside of a black hole, a 3D space, is entirely described by the 2D surface of its event horizon. It's a mind-bending idea that our universe might be like a hologram, a quiet suggestion that reality is far stranger and less dimensional than it appears.
Now let's return to the most famous paradox of all, the Fermi paradox, and explore some of the solutions in a little more quiet detail. Let's start with the rare Earth hypothesis. We talked about the long list of things that had to go right for Earth. Let's just sit with one of them for a moment: plate tectonics. On Earth, the crust is broken into large plates that are constantly shifting, grinding against each other, and recycling themselves, with old crust being pulled down into the mantle at subduction zones, and new crust being created at mid-ocean ridges. This process seems messy and destructive. It causes earthquakes and volcanoes. But it may be one of the single most important features for maintaining a stable climate over geological timescales. This conveyor belt of rock is a key part of the carbonate-silicate cycle, the planet's long-term thermostat. It pulls carbon-rich rock down into the mantle and then releases that carbon back into the atmosphere through volcanic eruptions. This cycle has regulated the amount of CO2 in our atmosphere for billions of years, preventing our planet from either freezing over or succumbing to a runaway greenhouse effect. But is plate tectonics common in the universe? When we look at the other rocky planets in our own solar system, we see no signs of it. Mars is a one-plate planet. Its crust is a single, solid shell that has been locked in place for billions of years. Venus is also thought to lack Earth-like plate tectonics. It might be an incredibly rare geological feature. It might require a planet to have a very specific size, a specific internal temperature, and a specific amount of water to lubricate the process. So it's possible that the galaxy is filled with Earth-sized rocky planets, but almost all of them are geologically dead and therefore unable to maintain a stable, habitable climate for the billions of years needed for complex life to evolve. The quiet, slow grinding of our own planet's crust may be one of our rarest and luckiest assets.
Let's now consider one of the more unsettling solutions to the Fermi paradox in more detail. This is the dark forest theory. The core of this idea is a chilling piece of game theory applied to galactic civilizations. The analogy of the dark forest is a powerful one. Every civilization is a silent hunter. They know the forest is full of other hunters, but they do not know their intentions. Are they peaceful? Are they hostile? Because the distances between the trees, stars, are so vast, communication is slow and difficult. It's impossible to establish trust. Any civilization you contact could be a potential threat. And if they are more technologically advanced than you, that threat could be existential. In this scenario, two fundamental truths emerge. First,
every civilization wants to survive. Second, every civilization is a potential threat to every other civilization's survival. So, what is the most logical course of action to guarantee your own survival? You stay absolutely silent. You do everything you can to hide your existence, to erase your own signature from the cosmos. And if you are foolish enough to detect another civilization that has revealed itself, the safest possible move is to eliminate it before it has a chance to eliminate you. This theory paints a very different picture of the Great Silence. The sky is not quiet because it is empty. It is quiet because everyone is hiding. Our own SETI program, our attempts to listen, is like holding our breath and straining our ears in the dark forest. But our attempts at METI, messaging to extraterrestrial intelligence, where we have sent out powerful radio signals like the Arecibo message, are, in this view, the equivalent of shouting, "We're here!" at the top of our lungs. It's a sobering and deeply quiet thought that the silence we hear might be a carefully maintained and very prudent state of fear.
Let's now drift to a less fearful but equally profound solution. This is the idea that they are too alien to recognize. This is a powerful antidote to our own human-centric biases. We are, after all, just one example of life, and a very recent one at that. Why should we assume that all other life, especially life that might be millions or billions of years older than us, would follow the same path? Our search is based on looking for things that look like us. We look for Earth-like planets. We scan for radio waves. But an incredibly advanced civilization might have long since abandoned its biological roots. Imagine a civilization that is transitioned into pure machine intelligence. They would not need a watery, temperate planet. They might find the cold vacuum of space near a reliable energy source to be a much more efficient and desirable home. They might exist as vast, silent computational structures orbiting a star, or even a black hole. We might be looking at one right now and not even have the framework to recognize it as a sign of intelligence. Or perhaps they have mastered physics to a degree we can't even imagine. Maybe they live in other dimensions or have learned how to manipulate space-time itself. Their technology would not look like technology to us. It would look like physics. It would look like a natural part of the universe. And their communication might be just as alien. The idea that they would use something as primitive and inefficient as radio waves might seem as quaint to them as us expecting them to communicate with smoke signals. They might use modulated neutrinos or gravitational waves, or some other channel that we are completely deaf to. The galaxy could be alive with conversation, a constant hum of information exchange between ancient civilizations, and we are simply standing in the middle of it all with our simple radio receivers, hearing only silence. It's a humbling thought that the silence might not be in the sky, but in our own limited perception. Let's quietly contemplate one last solution from this category before we conclude our journey. This is a newer, very clever, and deeply strange idea called the aestivation hypothesis. The word aestivation is the opposite of hibernation. It means to be dormant during a period of heat. This hypothesis comes from thinking about the fundamental physics of computation. Any form of computation, any thought process, whether it happens in a brain or a computer, generates heat and consumes energy. And a key law of thermodynamics tells us that the colder the environment is, the more efficiently you can perform computations. You can get more thinking done for the same amount of energy. The universe right now is in its stelliferous era. It is young, warm, and filled with bright, energetic stars. From the perspective of a hyper-advanced, likely digital civilization whose primary goal is to compute and to process information, this is a terrible time to be awake. It's an inefficient, high-energy, and wasteful era. The aestivation hypothesis suggests that the most logical thing for a very advanced civilization to do is to go to sleep.
They would gather resources, set up their systems, and then enter a state of dormancy, a cosmic hibernation for trillions of years. They are waiting for the far, far future, the degenerate era, when all the stars have burned out and the universe has cooled down to nearly absolute zero. That cold, dark future will be the perfect, most efficient time for computation. An almost infinite amount of thinking could be done with a finite amount of energy then. So in this view, the sky is silent because all the truly advanced civilizations are currently asleep. They have set a cosmic alarm clock for a few trillion years from now and are quietly waiting for the universe to get colder. We are like children, born in the heat of the day, running around and making noise, while all the wise old adults are taking a very, very long nap, waiting for the cool of the evening.
And so we have reached the end of our long, quiet journey through the labyrinth of cosmic paradoxes. We have wandered from the strange, flexible nature of time in the twin paradox to the simple, profound question of why the night sky is dark. We have stood at the edge of black holes, grappling with the loss of information and the strange simplicity of their nature. We have zoomed out to contemplate the very structure of our universe, questioning why it is so flat and why its expansion is speeding up. And we have ended with the deepest and most personal paradoxes of all, the quiet, unanswered questions about life and our own existence. Each of these puzzles is like a beautiful, intricate knot in the fabric of our understanding. They are not frustrating dead ends. They are the exact places where science is at its most exciting. They are the signposts that point towards the next great discoveries, the next revolutions in thought. They are the gentle whispers from the universe that tell us, in no uncertain terms, that our picture of reality is still deeply, wonderfully incomplete. There is a deep comfort, I think, in accepting that we do not have all the answers. The universe is not a simple story that has already been written and that we just need to read. It is a grand, unfolding mystery, and we are lucky enough to be here for this brief moment in cosmic time to be able to witness a small part of it and to ask these wonderful, profound questions. The beauty is not always in the solution, but in the quiet, patient contemplation of the puzzle itself. The awe is in the mystery.
So, as you settle into your final moments before sleep tonight, let these quiet paradoxes be a soothing presence. Let your mind drift with the image of the two twins, one old and one young, a testament to the strange nature of time. Think of the darkness of the night sky, not as emptiness, but as a sign of the universe's own birth and its grand, ongoing expansion. Contemplate the quiet strength of the rare Earth hypothesis and the profound preciousness of our own world. Or drift with the great silence and wonder if we are alone or simply listening with the wrong kind of ears. These questions are too large to be a source of worry. They are a form of meditation. They are a way to zoom out from our own small concerns and to connect with the grand, mysterious, and beautiful cosmos we are a part of. The universe is under no obligation to be simple or to make sense to our intuition. And in its strangeness, in its beautiful logical contradictions, we can find a deep and profound peace. The search for answers is a journey, not a destination. And tonight, our journey is at an end. It is time to rest. Sweet dreams.